Hello everyone, and welcome back. In this video we will discuss two types of lateral force resisting systems, the moment frame and the braced frame. And to help us understand how these systems work without relying totally on mathematics, we have our handy MOLA model. Using this model we can demonstrate how each of these systems actually provides resistance against lateral loads. We can also make a rudimentary assessment of how well each of these systems performs under loading by giving them a shake test. So let's start with what I have in front of me right now. This is an example of a simple gravity frame consisting of two columns and a beam, connected entirely by pinned connections. In other words, no bending can pass through these joints. As you can see, this model performs perfectly well under gravity loading. That is, it can sustain its own self-weight without collapsing. However, when I apply lateral load by shaking the foundation, you can see the structure starts to deform. And if I were to remove my hand here, it would collapse. So how can we provide stability to this structure under lateral loading? Well, notice in this deformed state how the angles between the members have changed. These two angles have increased dramatically, while these two have shrunk by the same amount. So what if we were to stop that kind of distortion from happening? Let's give that a shot. Here I have some triangular magnets that I'm going to clip onto these joints. And these clips are going to make these two joints now fixed instead of pinned. In other words, bending forces can now transfer through these joints. And now as I apply load, you can see that the angle between the beam and the columns at the joint remains at 90 degrees, even as I push and pull on this frame. Note also what is happening to the rest of the structure here. Both the columns and the beams are distorting. We can see this most clearly in the columns where the rings on one side are spreading apart and on the other side they are squishing together. In other words, we have tension on one side, compression on the other. This type of distortion is of course known as bending. And I can give you an even better look at that distortion by using this piece of foam here. So if I take this piece of foam and I apply the same conditions to what was happening to those columns, in other words, there's going to be a pinned condition down at the bottom, so I will allow this hand to rotate. However, I'm not going to allow it to translate back and forth. And then vice versa with this hand, it will remain locked against rotation. However, it will translate laterally. And as you can see, what's happening here, similar to what we saw with the columns, but now on a much larger scale, you can see we have tension on one side, compression on the other. In other words, bending. So fixing these two joints was a success. We created a frame with lateral stability. When I push on it and let go, it more or less returns to the same original position. This frame locks the joints between the beam and the columns, enabling bending moments to form within the members. This reliance on bending in the columns and in the beam is where a moment frame gets its name. Now, let's give this thing a shake. As you can see, it wobbles around quite a lot, and this really shouldn't be much of a surprise to us. We know intuitively that bending forces are very difficult for a structural member to resist, especially long and slender members like columns and beams. So how could we make this moment frame stiffer? In other words, how could we reduce how much it shakes? Well, we know that bending resistance increases with depth, right? bending this foam in this direction is a lot easier to do than bending it in this direction. Again, because the depth is greater when we orient it this way compared to this direction. So one option could be to increase the depth of these members in their plane of bending, like this. So these columns would get wider, and this beam would get deeper. And that would certainly be a valid solution. However, unfortunately, I don't have the means to do that with this model, for one. And also, architects usually don't like the idea of wider and deeper structural members. So let's try a different approach. Of course, what I'm showing you here is just one frame. And in the actual context of a building, we would likely have many more frames. So we would likely already have other bays with gravity framing like this. And if we wanted to increase the stiffness of this whole line, we could just continue adding these fixed connections, right? So instead of having just one moment frame, now we have two. So now we have a second moment frame added here. Let's give this thing a shake again. And as you can see, it still wobbles around quite a bit. So I'm not really happy with that amount of wobble. So can we make it stiffer still? Well, unfortunately, I've run out of these little foundation elements, and I've run out of room on this board, so we're not going to be able to add another row of moment frame. So instead, I'm going to have to try something that would only ever really be considered as an absolute last resort in the real world of structural engineering. As you can see, we have already fixed all these joints up at the top here. And you might have been wondering at the start of this video, well, why haven't we fixed any of the joints at the bottom? Wouldn't that provide lateral resistance? Well, yes, technically you're right. Adding these pieces here would provide greater lateral resistance. However, it's important to note that just because you can do something very easily and very simply in a model doesn't mean that it will be quite as easy or simple to do it in the real world. So in this model, fixing these joints down at the bottom was very simple. All I had to do was snap those pieces into place and it's done. I've created more fixed joints. However, in the real world, what we have below these joints isn't a nice solid piece of magnetic metal. Instead, we have this soft, compressible, unpredictable mess of soil. And creating a fixed condition in soil is extremely difficult and costly. So we only ever do it when we absolutely must, as is the case here since I ran out of parts. So without further ado, let's give this a shake. And as you can see, it's not really moving around much at all. Success. If I apply a static lateral load, you can see a little bit of distortion, but not nearly as much as what we were seeing before. So I call this a success. Alright, now let's move on to the braced frame. Alright, so we're back to our simple gravity frame here. Now, we know that a braced frame behaves very differently from a moment frame. Rather than relying on the bending resistance of the beam and columns, we instead pass all of the lateral force directly into this brace. Now, all of the joints in a braced frame are going to be pinned, as opposed to fixing the joints with the moment frame. So, in the case of the braced frame with all pinned conditions, there will not be any bending whatsoever in any of these elements. Now, it took a lot of extra material before we could get our moment frame system to stop shaking so much. Let's see how many of these braces it takes to achieve that same level of stiffness. I'll start with the first one here. And let's try applying force. Already you can see it's not going anywhere. Even if I push on it in this direction, this thing is not moving. Even if I shake it, there is no movement whatsoever. Of course, we shouldn't be that surprised by this. If you imagine holding a long stick in your hand and someone asks you to break it, would you do so by pulling on it or by bending it? Of course, you would bend it. And it's the same thing with these two lateral systems. A moment frame is going to be significantly weaker by the nature of how it provides resistance through the loads. It provides resistance through bending in the members, whereas a braced frame acts completely axially. So it's similar to trying to break something by bending it versus trying to pull on it. So hopefully that explains visually just how much more efficient a braced frame is compared to a moment frame system. Remember, we had to add all of these joints plus an extra row of columns, and we had to complicate the foundation just to achieve what the braced frame could do with this one skinny little strand. So when it comes to cost comparison, generally braced frames are far more cost efficient compared to moment frames.